All right, nice to see so many of you. Is this picking it up? I'm sorry, I'm the worst at these. Okay. Sorry, Panopto listeners. Did that do it? Is it picking up my microphone in the back? Can you hear me in the back? Is it projecting back there? Okay, based on no one's response, I think the answer to that is no. Okay, let's try the podium mic today. Oh my God, the podium mic is worse. It's so tiny. Do I have to put this like right under me? Okay. Sorry, Panopto listeners, if that was really annoying. Okay. All right, how about that? Can we hear my voice projected in the back? Can somebody give me a thumbs up if the microphone's working? Can nobody hear me? Is the microphone not working in the back? Can anyone, okay, yo, in the back, can you hear me? Is the microphone getting picked up out of interest? Is the microphone not happening? Yes, it is? Okay, kind of. Why? Why microphone? Is this better? Did this do anything differently? Can you hear me now? Yeah? Okay, thank you. Thank you, somebody, for responding in the back. Okay. Sorry, honestly, I know I have a really loud voice, and so it sounds like I'm projecting up here. So if you can't hear me in the back, I'm going to need you to, let me know, okay? I see a bunch of confused faces. Is it being amplified back there? Yes? A little bit? Okay. Okay, I'm going to do this. Did that make it better? Yes, thank you. Okay, thank you. I did just go back and watch some of my recordings, and I know I peak on the mic a bunch, which is really annoying if you're listening with headphones like I was. So I'm sorry, Panopto listeners, but apparently I have to turn the microphone all the way up. Okay, it's 3:32, so let's get started. Here is your warm-up, and I messed up the animation. So guess what? You get the answer, and I'm just going to walk you through it now. We're behind anyway. So, okay. Today is a very mathy day. I'm just going to be really honest with you, but if you've taken a chance to look at exercise number 2, then you can see that exercise number 2 is half about analyzing recursive code, very mathy, and half about hashing, which we will start on Friday. If you go to section tomorrow, which I highly suggest, you're going to get a lot more practice of the things we're talking about today, and they might even introduce you to hashing a little bit. But everything on your exercise 2 that has to do with analyzing recursive code, we're going to go over in lecture today. So let's talk through this. I'm sorry I sort of revealed the answer here thanks to the animations, but there's been a very understandable amount of confusion about why is the worst case not synonymous with big O. So remember that big O, big omega, and big theta are asymptotic analysis tools to evaluate the runtime of a specific function as n tends towards infinity. Case analysis is how to look at code with branches and determine what runtime function may happen based on the results often of an if statement. So you can apply asymptotic analysis to any runtime function. Case analysis means you might have multiple functions to represent the same piece of code like we have here. Now, I did have to pull some stuff in from later in the course to even invent a piece of code complex enough to give you an example, but the stuff I pulled in is hashing, which will start on Friday, so we'll call it a foreshadow. So let's take a look at this piece of code. This code's called mystery, and you can see what it does is it takes in a value n and then a set called primes. And the set is in something called a hash set. And what a hash set is a unordered collection of data that gives you the quickest possible lookup time. So let's walk through and try to create a code model as we've been doing. And if you remember, the basic approach is I always start with what I think of as sort of the basic operators, and then I work my way from the inside out. So here's maybe some of the, quote, basic operations. We have an if statement that checks if primes contains the value we were given n. I'm going to talk about that in a second. Then we have a return statement, +1. In the else statement, we have an assignment, there's a +1. We've got some tests. We've got all of this sort of math, so on and so forth. And then at the very end, if we did not find, or if this thing was in fact a prime number, meaning we did not find a common divisor, then we return true, but we also add that prime to our set of primes. This is technically a form of optimization that we're going to talk a little bit more about later too, called dynamic programming. And what we're doing is we're sort of, as we compute things, remembering what we compute for a possible later call. So really what's happening in this code is I'm asking you to tell me if the number I give you is a prime number, but I'm keeping a memory of every time I've computed a prime number, so I don't have to recompute it later. So that will save me time. And what I'm doing is I'm saving those things in this magical thing called a hash set, which actually runs in constant time for lookup. And I'm going to tell you how we manage that magic on Friday. But what this essentially means is, remember that is prime code where we sort of have that O of linear, but that omega of constant? Where that comes from, remember, is that if something has a quickly found divisor, like it's an even number or it's divisible by 5, we hit this if statement in here and bail out. Otherwise, if it is a prime number, it takes all of these while loop iterations to determine that there are no divisors. So the code will run longer in pursuit of a prime number because we have no way to interrupt the loop and bail out early. So you can kind of start to split this now into best case and worst case along the lines of these branches. Best and worst case often are related to branches. There's often some if statement that if true, you don't complete the iteration, or if you just look something up in a collection. And so if you think about trying to graph this thing, and I'm sorry, I drew the graphs and they look like I drew them, but let's take a peek. Let's imagine that the red up and down line, that's everything that's happening in the else case. And that should look a little familiar from, I want to say, lecture 4, where we talked about is primes, where every sort of entry up here, that was a prime number that took all of those while loops to get through. And the bigger the prime number, the more loops we have to get through, right? So that's why if it is a bigger prime number, it's increasing in a linear way for us to determine if it's prime. But if it's like an even value, that's just always going to stay constant. We just bail out really fast. Because if it's mod by 2, we just bail out, and it doesn't matter how big that n is. And so that's how we get this sort of difference between an O and an omega. But that is all for the worst case scenario, which in this situation is, I've never seen this prime before. Versus the best case, where we had seen the prime before, and it was stored in our hash table. Yes, question? So in the scenario you are suggesting, what we are doing is not, our value of n is, we've got actually sort of two n's in that situation, where we've got an array that's a collection of values to check if they're prime numbers. This is an example of what if we were just giving you a single number prime to compute. So in that case, that's another meta level on top of this. So all this is going to happen for any time we determine a singular prime number, but if we have an array of a bunch of numbers to determine if they're prime, the best case scenario would probably be either they're all even numbers, or they're all like quickly discernible not prime numbers, or they're all prime numbers I've already seen before by the time I get to them. Because those are different branches right within the code that I might hit. And the worst case scenario is that as I compute all of those prime numbers, every single one is a prime number that I'd never seen by the time I get to it. Questions? Yes?
It is the math of square root, and we provide
Oh, this while loop test here, yes. So why is it O of n and not O of square root of n? Because square root of n is a coefficient, so I am simplifying so that this is all just still within linear. So, yeah. It's just a it's just a coefficient on n in that context. Yes, question? So, if you graph this, the square root of n, it still looks like a linear n, but n squared, because that's an exponentially growing function, will have that sort of growth rate. So they're just different complexity classes. I mean, technically you could run this while loop up until n as well. You'd just be doing some somewhat unnecessary calculations. We're stopping early at the square root of n because apparently if you haven't found any divisors between 2 and the square root of the thing you're looking for, then you're not going to find any future ones. That's some math stuff that I just borrowed from the internet. Yeah? So, was there no big theta? There is no big theta in this case, exactly. Now, to be extra annoying, the best case scenario has its own function, right? So the reason I wanted to show you this thing is there's this really tiny little green line here. It's kind of hard to see there. I'm highlighting it. That is the graph of the best case scenario. Because the best case scenario, if you notice, it's not based on a value of n. It's not like when n is less than 1,000 or when n's are mod. It's just, have I seen this before? Which is not relating to any of the axes on my graph, right? So because I can't partition that out, I have to graph it as n tends towards infinity. It's its own situation. So that runtime function, that does have a theta because it's big O of constant, omega of constant, so its theta is constant. But the worst case scenario, this red line, just like our friend said, because its simplified tight big O is different from its simplified tight omega, the theta does not exist. Any other questions on this? Yeah? Sorry, why is it theta of 1 for the best case? Sorry, the which one? Best case. Yes, what about best case? Is it theta 1? Yes. So the best case, because the simplified tight big O and the simplified tight omega are in the same complexity class, the theta exists, and theta is constant, or theta of 1. Yes, thank you for clarifying. Other questions? Yes? For the worst case. So the theta doesn't exist in the worst case because the simplified tight big O is in the linear complexity class, and the simplified tight omega is in the constant class. Thus, there is no fit line. It's too disparate. So the green line is the best case. The red line is the worst case. And then I did asymptotic analysis on top of those two different functions. I know. It's a lot to unpack. Yes?
Just to be very clear,
sure.
If instead we removed the dynamic programming part and we made the hash set in just the first 1,000 prime numbers, then would we not have a best and worst case and just have the normal?
Okay. Let's say we did this code a little differently, where my optimization was as I see values of n, so I don't know what values I've seen so far, so I can't determine where on the graph. If instead I did something where I was like, I just pre-computed the first 1,000 primes or something like that, then n under a certain amount, whatever I computed up to, would be constant time. But since that n is then limited, we can't really do asymptotic analysis because n doesn't tend towards infinity there. So that graph would be something more along the lines of, let's see if I can make this happen, then that graph would look like, are you going to let me draw? Oh, there we go. Man, Microsoft Whiteboard, every single time I try to use it in class, it does this to me. It freaks out. So in your example, what we would maybe have is, let me draw, please. Please? Come on. The indignity. Somebody shout at Microsoft about that. It works fine when nobody's watching. There, thank goodness. Okay, so never mind, I give up. It would start constant, and that at whatever value of n, then it would start to do its thing afterwards. And by our definition of big O, we would sort of ignore the growth rate before that constant of n. Sorry, I couldn't draw it. Yeah, question.
What if this was like a recursive method where never mind.
I love it. No, please finish your sentence because you have the perfect segue. Maybe it is something we will cover in today's lecture called Analyzing Recursive Code. Huzzah! Are we all sufficiently terrified by this annoyingly complicated thing? Do we want to add more on top of it? Huzzah! Let's get into it. So let's talk, that's not what I want. Let's talk a little bit about some announcements, and then we're going to talk about how to analyze recursive code. Because our friend is probably very accurately noticing that everything I've told you so far is almost impossible to do with recursion. So just some reminders, of course, P1 Dex is out. It's due tomorrow. Exercise 2 is out. It is due next Tuesday. And then also a super fun announcement, our wonderful community team has decided to put together some social happy hours where they're just chances for you to come together in person, drink some hot cocoa, maybe meet a new partner, and talk about some things that we just know are plaguing students. We're going to have, I think, at least 4 of them throughout the quarter. We'll announce what the different topics are, but this first one will be this Thursday from 3:30 to 4:30 in the Allen Center. That's that computer science building. It's the older computer science building in room 403. And the topics will be what 300 level courses to take after this, and then also how to deal with imposter syndrome, because everybody feels imposter syndrome, I promise you. Any administrative questions? Cool. Okay. Let's talk about recursive code. So, I have broken this lecture into roughly 3 recursive patterns. Now, before we got into all of this like terrifying math stuff about big O, once upon a time we probably saw like a singular for loop and knew that was linear, and a nested for loop and was like, oh, that's probably n squared, right? We sort of had these high-level patterns we were used to. This is my attempt to give you some high-level patterns for recursion, and I'm going to explain what each one means. So the first pattern is what I kind of refer to as having the input. And the best example I can come up with is binary search. Remember, binary search is when you have a sorted list, like a dictionary, and you're trying to look something up. So you probably start at the middle, and you look at whatever value's in the middle, and you say, does the thing I'm looking for come alphabetically before or alphabetically after? And then based on which direction, you sort of eliminate 1/2, and then you cut to the middle of the middle you just divided, and then you cut to the middle and the middle and middle again. In fact, let's talk about an animation. So let's say we have an array of values, and you notice they are in sorted order, and I am searching to determine if the value 42 exists in this collection. So what I'm going to do is I am going to maintain 3 separate variables. That was in the code on the last page. You'll see that code again in another slide. And I am going to look, and I'm going to say, is my value 42 greater than the min, less than the max? So is it somewhere within my range? And then I'm going to ask myself, is it less than or greater than the mid value? And right now, the mid value I'm comparing it to is 30. So I know that 42 cannot exist in this half of the list. I just sort of eliminate it. Now I only have half of the list left to consider, and I move my min and mid value, and now I look at my new mid value, which is 56, and I decide, is 42 greater than or less than 56? It's less than, so I can eliminate that half of the possibilities. And this time, I move my max and my mid. And now I'm looking again, but now I happen to have my mid be the exact value I'm looking for, 42. So I found it, which is great, because if you notice, I technically only compared 42 against 3 values that entire time. Very different than if I started index 0 and was like, is -4 42? Is 2 and 42? And so on and so forth, and did a linear search. So that's just the algorithm of binary search. The important thing to take away is us eliminating half of the possibilities each time. So the little white scope of where I am looking shrinks and shrinks in a logarithmic fashion, foreshadowing. Does anyone have any questions on how the algorithm works? So the binary search runtime ends up being logarithmic. The reason for that is because the time it takes, the amount of things I'm considering is reducing over time. And so as we grow in value of the total number that we start with in that array, the size of the half that we eliminate also grows. And so as we get to larger and larger and larger values of n, the difference in running this code starts to shrink because we immediately eliminate half of the possibilities. So even as n gets bigger, we so quickly reduce the amount of things we have to loop over that actually the runtime doesn't grow very quickly, even as n tends towards infinity, which makes logarithmic time a really preferable runtime if we can accomplish it. So let's now apply the ideas of case analysis to our binary search. So remember, case analysis is not about how many things exist in the collection, but the state of the collection. So remember that example where we were looking for 42? If you could wave a magic wand and pick the perfect, the most optimal place for the thing you happen to be looking for to exist at, where in that collection would it be? To reduce the amount of instructions I have to run, where is the ideal place for that 42 to have originally sat in that array? Yeah, there. Directly in the middle. Because that was the first thing I checked, right? So wouldn't it have been gosh darn convenient if the 42 was right in the middle? Again, not about asymptotic analysis, doesn't matter how many things were in that, it's just about the state of the data. So that would have been a constant runtime because I would have done one check and then bailed out, and technically the O, the theta, and the omega, all constant, just that one look. Okay, now, what about the worst case scenario? Where would have been the most inconvenient place for that 42 to have existed or not have existed? Any suggestions? Yes? At one of the extreme ends, right? Because we were sort of always looking in the middle, right? That definitely would work. Yes? If it's not in there at all, absolutely. And those two things, if you can imagine, kind of result in the same runtime because of the way we were looking. Now, if there was somebody like me in the class and was annoying, and they'd be like, but professor, couldn't you add an optimization where you also check if the thing is the min and max each time? Yeah, and you'll find a lot of times when people implement binary search, they do it for that reason, but I didn't add those optimizations. So both of these things fall into what we would call the worst case scenario. Maybe it's not found, i.e., the last possible location that I would have to check. And that is all logarithmic. So the best case scenario has a big O of constant. The worst case scenario has a big O of logarithmic. Questions? Yes? Great question. Would that be even worth it to check the min and max? Because technically then at each iteration you're doing 3 checks instead of 1 check. We're now in our balanced state. So if this was for a set of data that was massive, you'll probably find that 3n versus 1n, context and that checks is sort of negligible. But that's why you'll see that optimization not added in a lot of the academic code, because we're usually talking about scale, where you're right, 3 checks would be astronomically different than 1 check. So it's all about the balance. And at scale, that cost might be worth it. Great. So here's that code again. Hopefully we kind of understand how this code works. I hope the logarithmic stuff, maybe it doesn't sit in your gut naturally, but we get that sort of logarithmic growth. But I'm going to show you how to prove it's logarithmic growth now. So the thing about binary search is it's recursive code. Let's try to model this code like we have been approaching code modeling so far. So the first thing we do is I am a procrastinator. And I am terrified of recursion. So I'm going to start with the non-recursive stuff. And remember, in any recursive problem, you always have to have the base case, which is non-recursive, separate from the recursive case. If you don't have some non-recursive base case, that's how you get that Stack Overflow infinite loop situation. So here is some code models I'm applying to the base case, which doesn't have anything recursive in it, so cool. Now, if I'm looking at this, I just sort of went through, I'm like, oh, here's one check, one, here's a return, one, here's another check, one, here's maybe I access an array and do an equal, there's two, so on and so forth. But you can see this is still branching. So this is the base case, everything in this if statement here. The best case scenario within the base case is like I do this one check and then do this one return. But I am almost always looking for the worst case scenario because we are pessimists as engineers. Also because we usually have to account for worst case scenario in terms of how many machines. So that's why we're mostly obsessed with it. So the worst case, the absolute maximum number of operations I'm going to execute just within the base case, I'm always going to do this if check. But if that if check is false, then I'm going to come down here and I'm going to do this if check. And if that if check is true, then I'm going to enter here. And then I'm going to do this if check. And then I will either do this return or that return, which ends up being the same. So the absolute most amount of operations I might execute just within the base case is 5. I don't care about the number 5, but what I care is that we're starting to think about the branching and what's the absolute most number of instructions. But either way, the base case is just some constant number. Now, I've done the non-recursive entire case. There's the recursive case. But even within the recursive case, we can see that there's some non-recursive code. So I'm still trying to put off dealing with that recursion. So here is some calculations of the non-recursive stuff. So there's some, math at the top there, that +3. Then we have a check right there to see if we've magically found the mid. So there's some stuff there. So for example, we're always going to do this +3. Then we're always going to do this if statement. If that if statement happens to be false, then we're going to do this else if statement. And then we hit that dreaded recursion. And it's like, how do we put that into a math function? So the best case is maybe those 6, like we do this 3 and this 2 and this 1. The worst case is we do this 3, this 2, and then whatever the heck we do for the recursion. And guess what? Delightfully, there actually just exists mathematical notation to directly represent a math function that is a function of itself. In computer science, a method that calls itself is called recursion. In math, a function that calls itself is called a recurrence. Helpful. Will I mix up those two words at some point? Yeah, I'm sorry. But here's how you would represent this. This 5 up here represents the base case. And then I just straight up kind of copy that if check. So I've got sort of like one function up here for when I hit the base case. And then down here, I've got the work that's non-recursive, that's that +7, plus a call to myself representing how the input will change. I'm going to talk a lot more about this notation, but hopefully you can kind of see these pieces represented in this mathematical notation here. This little curly brace, as I think of it, is the notation for how to write a recurrence. So you can write a mathematical function that is a function of itself. So yes, meet the recurrence. It looks a lot like recursive code. Here is my attempt at trying to formalize it for you, where you have f of n is equal to the base case on top, and then if the base case test is when that function happens. And then on the bottom, you have the number of recursive calls times the recursive mathematical function, where you pass in however n is reduced towards the base case, and then plus some non-recursive work. And remember, for recursion to work, the recursive cases need to alter the input in some way. Otherwise, we're just doing the same thing in the same method over and over again. You get that Stack Overflow error. And to make sure that your recursion ends, the way you alter the n in the recursive case has to tend towards that base case test. So this base case back here is if high is less than low, meaning I need to be reducing those numbers, reducing them down, so I can eventually make that true and end the recursion. So that's what we're putting in the parentheses of the function, however n is reduced in the direction of the base case. Let's do it with hopefully some more directly applicable code. So go ahead, take, let's say 3 minutes with the people around you and try to write the recurrence modeling this piece of code. Start with the base case, then with the non-recursive work in the recursive case, and then write that recursive as a function of itself. Go ahead, talk for a couple minutes. Okay, take like 30 more seconds. Okay, let's start to break this down. So again, let's start with the least scary pieces of it, hopefully the base case. Does any brave soul want to raise their hand and tell me what their function for just the base case is in this situation? Yes, please. 2. Yeah, let's see if yeah, there you go. This is just sort of the non-recursive things. I agree with 2, where this if statement and the return, that's the entirety of the base case. There's sort of 2 operations in there. Looks good. Then, from this for loop down to this return statement here, that's the entirety of the recursive case. But again, we're procrastinating on the recursion. What is the runtime of the non-recursive work within the recursive case? Any brave souls want to raise their hand? Tell me. Yeah, here.
Would it be n by 6?
Let's see. That is a good question. So it's certainly n, and I assume, let's see. Yeah. N because we've got this for loop running from n. We've got a little bit of like things coming off the end here. Is the 6, are you getting the 6 from these divided by 3s over here? Yeah. Okay, great. We're going to talk about that. But yes, you are absolutely correct that the dominating term of the non-recursive work within the recursive branch is linear. Let's see where my animations go. So there we go. Base case, cool. So there's that n right there. And then we've kind of got like a little bit of extra there. So maybe like you could probably convince me of other numbers than that +2, but I kind of threw the +2 down here for here. So that's the non-recursive work. Okay. Now let's talk about the recursive pieces of this. how many recursive calls are there, and thus what will be the coefficient in front of the recursive term in your recurrence? How many recursive calls are there? 2. Yes, thank you, everyone. I saw a bunch of these. 2. There are 2. Now, how is n altered in each recursive call? What are we going to put between the parentheses on the recursive function within the recurrence? Yes. Divided by 3. So we would end up with 2 f of n over 3. So this is how I would extrapolate that out into the full recurrence, where I've just put that base case with the if check, the coefficient from the number of recursive cases, how n is altered, and then this n plus 2, that's for the non-recursive work within the recursive case. Questions? Yes? Yeah. Sure. Oh, like, is the divided by 3 important, or is that like one of the things we wave away? Is that what your question is? Would you add 2 to it? So that's where, yes, this is confusing. So you might want to say, like, algebraically distribute this, but we are going to leave this as 2 separate calls to f of n over 3. So how n changes per recursive call does need to be specific, and then how many recursive calls there are. So the 2 recursive calls stays as a coefficient here, and then how n changes, it happens to be divided by 3, so that's what happens inside the parentheses. Did that answer your question? We have further questions. Okay. Yes, question? Am I not counting the system.out.print? I'm counting it as 1 times n. So the 1 kind of just disappeared into this term of n. Is that what you mean?
Like as non-recursive work?
Yes, this is non-recursive work. So this whole for loop with the println inside of it, that's represented by this n right here. If there were 2 printlns, maybe you'd put a 2n. If there are 3 printlns, maybe you'd put a 3n. But there's 1 println, so we just put n. Yes, question? So the 2 here means there will be 2 separate function calls where n is reduced into a third. So this line here plus this line here, since there's 2 of them, that's where the 2 comes from. If there were 3 recursive calls, this 2 would be a 3. So that's where I'm representing it. The 2 at the end, sorry, that's just me, like this val 1 times val 2 plus a return. Just if there was like another, I don't know, bit of math in here and this was a plus 3, then it would be plus 3 on the end. So that plus 2 represents this line here. Yes? So the 2 comes from the number of recursive calls. The divided by 3, I'm just pulling that and how it's changing here. So we do not multiply anything inside these parentheses by how many times or anything like that. We leave those things separate. Okay, great. Yes. So, thank you. We will talk about other ways that you can alter the input. I'm going to start with this one because guess what? There's a plug-and-chug formula to find the closed form of this if it's in this format, but I will answer your question in a couple slides. Yes? Oh, thank you. Yeah, I agree. So you are technically going to hit that if statement, and so then that would be plus 1 there. And like if we were really into it, maybe we would count something in the for loop header other than the convention says we doesn't. So the reality is this +2 could even be like +20 or I don't know, but I kind of am like, it's a non-dominating term, and you'll see in a slide where it sort of doesn't matter. And if I ask you to do this on your exercise, there's even a big paragraph at the top that says, we don't care what this number is, we just care what the coefficient is and what numbers are in between the parentheses. Those are the ones that really impact it, but these kind of things, yes. So I agree with you, it's probably even more accurate to be +3 on the end there. Yes? Great question. We will get to that. So yes, if you can tell, there are some limitations in this because this is delightfully consistent within itself. But let's talk about how to go from this to actually finding the big O. Because the thing is now this is our code model. And previously, we would kind of look at our code model, and I know I would be like, drop the non-dominant terms and simplify and all that stuff, but your eyes were probably fast enough at this point to just be like, there's the dominating term. I can see the big O. It's kind of contained within that function, right? But this one, I can't really just like look at it and tell what the big O is. So the thing about analyzing recursive code is once you have this recurrence, you need to do a little more math to actually find what we would call the closed form, or you need to do a little bit of math in order to actually determine the big O. There are a number of ways to do it. Once upon a time, I took multiple weeks of this course to teach you all of the different methods to do this. But I have since decided that's a waste of everybody's time. If you are interested in it, all the slides are still at the bottom of this deck for how to do all the other mathy stuff and all of those wonderful questions about the different formats, like what if your code is doing something different per recursive call or if there's a bunch of different recursive calls. I'm going to show you one way to get the big O for when you have nice clean versions of code like I showed you now. But if your code doesn't fit into the format I just showed you, then you got to use one of the angry math ones at the back of the deck, which is why I save you from doing that on the exams. But now you at least know where to look those things up. So this is just one of the way we're going to use in this class to find the actual big O of a recurrence is we're going to use this thing called master theorem. Honestly, pretty self-aggrandizing name, but it is really convenient. And you literally just take a recurrence and you plug and chug some numbers, and it tells you what the theta is. But if your recursive code doesn't fit into this format, then you might need to do something called unrolling. And if it helps your brain, I just want to show you this. Unrolling just means write out of the function at the base case and then start to write out the function with different numbers counting up from the base case to see if you can just intuit the pattern. Some brains work this way. My brain doesn't work this way, but that method is technically called unrolling, where you just write the definition of the mathematical function over and over until you can intuit a pattern. The other way of doing it is something called tree method, where you draw out each of the individual calls that are triggered by your recursion, and then you do a bunch of math to determine how many recursive calls are triggered. And that's also painful and mathy, but both of these methods can apply to recursion in any format. So if you end up in a situation, go look at the slides at the back of this deck, you can solve anything. But let's talk about our nice, delightfully convenient version of recursion. So this is our code, our recurrence from the last few slides. Master theorem says if you have a recurrence in this format where there's some type of constant base case, and then you have a f of n over b plus some function where n is raised to c, then log base b of a, if that's less than c, you're in a theta of n to the c. And so you can see we just need to determine what the values of a, b, and c are for our recurrence, and then we plug them into these logarithmic things and compare them to c. So in our situation, can anyone tell me what is the value of a based on this current recursion? Yeah, there. 2, absolutely. It's just the coefficient. Okay, what's the value of b? Anyone? Yes, 3, because it's n over 3. That's our b. Okay, this one's a little trickier, but can anyone tell me the value of c for our recurrence? Okay, yeah, help us out again, friend. You are correct. You're correct. It is 1. Now there isn't a little 1 floating in the exponent of that n, but if you remember, anything raised to 1 is just itself. So this plus n plus 2, it's an order of 1n. It's sort of like you could almost put an imaginary 1 exponent floating there. So the value of c in this case is 1. Pop quiz. What if I didn't have plus n, I just had plus 2? Can anyone tell me what the value of c would be? Yeah. 0. Because anything raised to 0 is what? 1. So it doesn't add a factor of n. So if there's no factor of n, your c is 0. So thank you all. Then we just plug and chug. So log base 3 of 2, blah, blah, blah. It gives you 0.63. I plugged that into Wolfram alpha. So 0.63 is less than 1, which is the value of c. So we are in the theta of n to the c, but c is 1. So we are in theta of n. Plug and chug. I see some nodding. Questions about how to apply this formula? Yeah, sure. So the for loop is giving us this term of n, which is giving us a c of 1. If we took out that for loop, our c would be 0. So if our c was 0, it would, instead of falling into this top case, it would fall into this bottom case, which would be n raised to the 0.63, I guess. Is that what that is? I don't know. Yeah. Yes. Yes. Which was log n? So, if this was plus log n here, then you couldn't use master theorem. And you would have to use one of the angry things at the back of the assignment. Yes, I know. So if you are actually curious as to why this plug and chug works, here is me explaining it. But I have realized that when I read through the slide, a lot of people stare at me terrified, so I'm going to let you decide if you want to read this slide. Okay, it's 417. I just want to give you some of these patterns again. So that was me proving to you that binary search runs in O of log n time using master theorem. But here are some other patterns that are very common in recursion. So commonly, like merge sort, where we have a collection of things and we split it up and we split it up and we split it up and then we bring it back together. We're not actually reducing the input. We're sort of still dealing with the same number of things at different levels of recursion. So I call this constant input plus some work. So this one actually, you can follow that along. This is the recurrence. You can still apply master theorem, but we end up with n log n. So constant size plus some work, we end up with typically n log n. And then this final one, I'm going to let you read on your own time. This is like calculating Fibonacci. And this is part of why it is very rare. I have 2 minutes. Give me 2 minutes, please, please, please. This explosion of runtime where you can see here, we're making 2 recursive calls, but we're just subtracting a value, meaning we're not like dramatically altering how many inputs. We're actually going to get this sort of explosion of method calls because we're not really reducing the input very much each time. This is actually why recursion ends up being almost so commonly inefficient. I have never personally written a professional line of recursive code. Does that mean that you have to ignore recursion? Not entirely, because we're going to talk about dynamic programming for 2 days at the end of the quarter, where I'm going to show you a recursive pattern, and then we're going to apply a bunch of optimizations to where it's not recursive anymore. But you can follow through these slides, and you can see that I do a bunch of stuff. It doesn't fit. Great. And you can do all this math instead. You see what I was telling you? This is kind of gross. But you eventually get to 2 to the n, which is a really inefficient runtime. So there are your 3 recursive models. This should give you everything to answer the exercise 2, analyzing recursive code patterns. If this is still difficult, as it should be, go to section tomorrow for more practice. And come back on Friday. We're going to finally start to dig into data structures with hash tables. Arguably the Beyonce of data structures.